All right, dear students, we are going to do riders today. It's Euclidean geometry. You already know your Euclidean geometry. You know your theorems. So we have done theorem 1 to 7. And here now you'll be asked to prove some riders. There will be no numbers here to expect. So we will be talking about how to prove that sides are equal, or maybe if you have parallel sides, that are they prove that those two sides will be parallel. And a very important one is how to prove that a line is a tangent, as well as how to prove that a shape is a cyclic quadrilateral. So let's jump right into the content and see what it is that we have in here. So to start with, we're going to just prove some parallel lines and some equal sides and perhaps a few equal angles. So here is the question that we have. The main thing you want to see is that AC is the diameter. It's a very crucial thing to remember what a diameter does. And a diameter, once we have it, we know very well that it subtends an angle that is 90 degrees at the circumference. So that's the one good thing about a diameter right there. We were given the center of the circle as O, and look, we have a line from center. We have a line coming from center, and it's not just any line. It is actually bisecting that chord that is over there. So we can tell we are dealing with theorem 1 here. However, is the converse of theorem 1. So at this point, let's figure out what was asked. Before we go anywhere, please, if a line comes from center and it bisects the chord, we know that there will be a little 90 degree over there as well. So that is what we do. Well, before I do anything else, before I answer this question, I just want you to see how to prove lines are parallel. At this point, we want to prove that those two lines are parallel. But here are the skills that are there for proving that two lines are parallel. So you'll find they'll ask you lines that are, say, like these ones. There'll be two lines, say, for example, it's here A, B, C, D on your circle or wherever they are. And they want you to prove that AB is equal to CD. There are three situations you may find or you may use to prove. You may find maybe there'll be a line joining that one to that one. So if you by any chance manage to prove that an angle that is over there will be equal to an angle that is over there, then you're done proving that that thing is a cyclic, it's parallel lines. So if you can prove that X is equal to Y in this situation, let's say you manage to prove it, then you can conclude and say, therefore, as a result of all this, I can see that AB must be parallel to CD. Why are you saying so? Because you're noticing that angles that are supposed to be alternating are actually equal. Because what we know is that if we have a shape such as this, a Z, and then these lines are already parallel, we know that those two angles must be equal immediately. So at this point, you were not told it was parallel lines, you were just you proved the two angles to be equal. Notice the change in the reasoning, alternating angles equal. Well, it works exactly the same way if you prove something of this sort. Let's say your two lines that you are proving now are A, B, and C, D still. So if you have a shape such as this one, it will be wise for you to prove that angle and that angle. So if your X is here and your Y is over there, if you manage to prove that X is equal to Y by any of these Euclidean geometry means, if you prove that X is equal to Y, you can conclude that, well, AB must be parallel to CD then, because you are noticing that corresponding angles are actually equal. That's how you prove it. So it doesn't matter which one you have. If you by any chance, I don't like using this method, but let's say maybe you are using this one as well. You know, it can be that. You want to prove that A, B, and C, D are equal. Under normal circumstances, let's say if they were like this, we know that this angle and that angle will be supplementary. They will add up to 180. But at this point, we already know, let's say we don't know that yet. We want to prove that those two are parallel. So if you, using your Euclidean geometry methods, prove by any chance that X plus Y is actually equal to 180, then you are done proving that those two are parallel. Those are the three ways we use to prove. So let me just tell you the reason. Here you will say AB is parallel to CD because you notice that co-interior angles are actually supplementary. So you can say sup, or you can write the whole thing. supplementary. Okay, can't remember if it's an E or A here, there, you can check it on your own. Right, so those are the three things we use to prove that lines are parallel. Well, now that we have that information, let's quickly go back to where we were just a few minutes ago. So I need all the space here, need to start all over again. Now let's prove that those two lines are parallel. The method we use depends on what we have. At this point, we remember we have those 90s that I just erased. We know that this angle is 90 and that one is 90. I can already see I have to use this F right here. Once I see an F, I know I have to talk about corresponding angles being equal. But you have to first of all mention what's necessary, like for example, how B is equal to 90 degrees, and the reason being angles in a semicircle. And the fact that P2 here is equal to 90 degrees as well. It's a line from center. It's the converse, okay? Line from center to midpoint of chord. We know that if it's a line from center is going to the midpoint of the chord, we know that it will be perpendicular to that chord. Well, we are noticing that P2 is equal to B. In this situation, once you prove those two angles to be equal to each other, then okay, so after you prove that B is equal to P2 in this situation, you can now make a conclusion. You can say, well, as a result of all of this, it means OP here is parallel to BC, and you actually proved angles that are corresponding to each other. So you have to use that one, corresponding. You notice that corresponding angles, you can write and stop right there because this is a very long word. Corresponding angles are actually equal. So in the same breath, maybe you could calculate P1 as well, and it will still be 90 degrees for the very same reason. And then you prove that co-interior angles are actually equal, so, or supplementary, I mean. So you can also use that method. So carrying on to the second question, let's figure out what's what here. Now we were given a tangent. The moment you are given a tangent, PQB is a tangent. So here is a tangent for us. The moment you have a tangent, please notice that opens ways for your theorem 7, which is tan-chord theorem. So you can use that one, or you can say tan perpendicular to radius, depending on what you find yourself needing. So here you were told there was some given information. QS is actually bisecting BQR. What it means is that Q1 is actually equal to Q2. I can write that one and say this one was given to me. If I want to prove two sides to be equal, let's go and find the two sides. Please, the sides are QS, there is QS, and then there is RS, which is over here. So if you want to prove that those two sides are equal, you can actually enclose this. These are two adjacent sides. You can close them up and actually form a triangle. If you want to prove that these two sides are equal, please, these will be the angles you have to prove to be equal. So you need to have a game plan. So at this point, we already know if we manage to prove that Q2 is equal to R in any method possible, we will be done proving that QS is equal to RS. So we are proving two sides to be equal in this situation. Well, now that we know what we want to do, it's Q2 and R that we have targeted. Let me remove some of these lines so you can see what's going on. So what is it that we can do in this situation? Well, if you want to prove angles to be equal to each other, let's say Q2, you find angles that are equal to Q2, find angles that are equal to R itself, and then see if there is a relationship. There is one thing I want to immediately say here, using that same tangent that we talked about. There is a tangent, and if you want to calculate the angle between a tangent and a chord, let me just say I use this chord QS. The angle between the tangent and a chord in this situation happens to be Q1. Well, if you want to use tan-chord theorem, you practically have to hold both sides of that chord and draw it until you reach the circumference. The angle you form over there will be the angle that is equal to Q1. So immediately by doing that, I can tell that Q1 itself is equal to angle R. And I can say this is because I noticed it's tan chord theorem. Okay? So the moment that one is done, we have two angles that are equal to Q1 at this point. So I can easily say, therefore, Q2 itself is equal to R. Why is that? I am seeing that both of them are equal to Q1 in this situation. I don't have to write that one as a reason. So sorted, it's very easy to get this thing done. Right? That's your question 2. Let's quickly figure out what else you had on the... Oh, I didn't conclude. We need to conclude. If Q2 is equal to R, we need to now say, therefore, or as a result of all of that, QS, therefore, must be equal to RS. If we proved that these two angles are equal, the next thing we can say is that those two sides must be equal to each other. And please, there is a reason as well. You have to give us a reason. Why are you so sure that those two sides are equal? Because we notice that they are sides opposite equal angles. So we have that reason that we use for whenever we have a radii and we want to show that two angles are equal, and we say it's angles opposite equal sides. So it's the other version of that same reason. This one, you start with sides, is opposite equal angles right there. So that is question 2. All right, now let's quickly figure out what's happening here on question 3. On this one, we are going to prove angles to be equal to each other. So we want to see which angles it is that are asked here. So it's D1 and C. They didn't beat around the bush. They want you to prove that D1 is equal to C. That's our job right here. If you want to prove that angles are equal to each other, you don't go and try to prove D1 is equal to C immediately. Find angles that are equal to D1 in the same and this, and then find angles that are equal to C. Find out if there is a relationship on those angles. At this point, I can't help but to notice that D1 is equal to B1. So I want you to see that tangent again, that is here. I want to use this chord right here. The angle between that tangent and this one and the chord will be equal to B1. Like I said before, hold both ends of the chord and go to the circumference. So you're noticing that D1 must be the angle that is correct in the situation. So you can see that B1 must be equal to D1, and that is because of the tan chord theorem that we have already seen together right there. But I've seen that I'm talking about B1 and then D1, and I already have the D1. So what I'm going to try and do now is to try find angles that are equal to C. So because I already see it, I'm not going to have many other options. So I guess when you are doing it for the first time, you have many angles that you found that were equal to D1, and most probably you have many angles that are equal to C. Find the ones that have a relationship. So at this point, I want you to draw your attention to the parallel lines that we have. I'm going to find angles that are equal to C right now, and also that line. I believe you're seeing the letter F right there. And if you're seeing F, it means you can appreciate that they are corresponding angles, that C and that B1. So by doing that, I can really say, well, angle B1 as well is also equal to angle C. And I am using the fact that these are corresponding angles. And you see the difference in the way we phrase our reason. Here, the lines are already parallel, and hence we are actually writing it as a reason like this. So at this point, both D1 and C are equal to B1. So I can really conclude and say, therefore, D1 must be equal to C, because they are both equal to B1. If you are that person who is afraid, you can write both equal to B1 but it's not a recognized reason at all. So please people, that was all. You proving angles to be equal to each other. Find an angle that is equal to the first one, the angles that are equal to the second one. You may have to do 2 or 3 steps before you get to the answer, but we're just at the beginning of riders, so I can give you a break for a while. So let's quickly figure out what we have here on this question as well. So we have a cyclic quadrilateral. A cyclic quad is an interesting thing because we know if it's a cyclic quadrilateral, opposite angles are supplementary, as well as exterior angles being equal to opposite interior angles. That is what we know about a cyclic quadrilateral. So we have one here. So let's see what we are required to prove. However, we want to prove 2 sides to be equal again. The first thing we do is to go find them. So it's DC, which is this side, and then DC, and then DB, this side. Well, again, there are 2 adjacent sides, and you can see you can close it and form a triangle. And you can see if you form a triangle, it will be this triangle right here. So if you want to prove that these 2 sides are equal in any way, or if they were equal, if those 2 sides were equal, it means this angle and that angle were supposed to be equal. That's how you figure out what to do. So in this situation, you're noticing you have to prove that B2 is equal to C1 plus C2. That is the game plan you have over there. If you can prove that B2 is equal to C1 and 2, oh, don't worry, then DC will immediately be equal to DB right there and then. So let's quickly find out what's what. Let's erase everything and start again. Now, how am I going to prove that B2 is equal to C1 and 2? So you may try find angles that are equal to C1 and 2, or angles that are equal to B2. It's your own thing. Now, at this point, I am noticing that we have an angle that is crying and equal to C1 and 2. Please remember we have a cyclic quadrilateral. Our cyclic quad is still here. And the good part is that we have an exterior angle. This angle A1. From what we remember, that exterior angle, which is A1, must be equal to the opposite interior angle, which is this one. So A1 is equal to C1 plus C2. This is because it's the exterior angle of a cyclic quad. Okay, that is us saying A1 is equal to C1 plus C2. Perfect. Now, what else do we know? You know, I want to just draw your attention to the given information. We were told that AD bisects EAC like this. This angle right there. If we were told that, by knowing that, we know that A1 is actually equal to A2. This information here was given to us, that A1 is equal to A2. The interesting part about that information is that immediately after you tell me that, I can see that A2 at this point happens to be equal to B2. If you don't see that, let me help you to see why they are equal. I'm going to erase everything. Now, you remember the theorem we normally would call the bow tie. If you want, you can see that this angle right here, B2, was subtended by DC, as well as this angle B2. It was subtended by DC over there. So these 2 angles are definitely equal to each other. And that is because they are A2 is equal to B2. These are angles in same segment. Okay, so I hope you are seeing the flow here. I just mentioned A1 was equal to A2, and now I'm saying B2 is equal to A2. Notice how, as a result of these 2 statements here, there are 2 angles that are both equal to A2. I think I can write it and you all can see. It means A1 itself is equal to B2. Okay? A1 is equal to B2. Can you see that we can conclude that? if A1 is equal to B2, I can now take this statement and come back there. In place of A1, I can put B2. So I can conclude and say, well, since that is the case, as a result of everything, in place of A1, if I put B2 in that one, it means it will be B2 is equal to C1 plus C2. And that is what I wanted to prove. Well, we are running out of space, but we can write on this one. If I prove that B2 is equal to C1 and C2, I can now conclude that DC must be equal to DB. Therefore, DC, I hope you can see this, is equal to DB. Excuse me. And these are sides opposite equal angles. Like that. So that is all you do with this question. Well, now that we have sorted that one out, let me show you a different skill altogether. So there are also things that we don't only prove angles to be equal or sides to be equal or parallel lines. We also have more interesting things such as proving that a thing is a tangent. It's a very good thing to know. How do we prove that a line is a tangent to a circle? It works like this. They will say to you, prove that AB, in fact, for you to understand better, why don't I do this? If this was, I'll just use my free hand here. So let's say we had a circle over here. And there was a tangent, a real tangent that we knew. And then there was a chord, and then the chord was subtending an angle at the circumference. The one thing that we were going to be very sure of was that this angle A1 was going to be equal to angle B. That is what we know. A1 will be equal to angle B. And we'll say tan chord theorem like that. So what they will do this time is that they will remove the circle. The circle won't be there anymore in this situation. And there will be a letter here, of course. Let me call it C. And normally, this one will just come from one side. Let's say from that side. I'm going to put a point P here. The question will say, prove that AP is a tangent to the circle passing through ABC. And when you look there, you will see no circle there. And that you will see a triangle instead of a circle when you're looking at the whole thing. The main thing is that you have to know which angles you have to prove. So if you by any chance can prove that A1 is equal to B, if you are in a situation like this, notice the tangent will be this one, right? The first time it touches the shape will be right here. So the angle that it forms when it touches the shape will be the same one that it should form on the other side. So if you can prove in this situation that A1 is equal to B, you're sorted. Okay, they can also do this. Prove that the tangent, let's call this tangent PT, is, prove that line PT is a tangent to a circle passing through those 3 points. T, let's just say Q, R here. So the question will be like, prove that PT is a tangent to the circle passing through TQR. You don't see a circle, you don't see anything over there. And then what you do is you're going to go to the time when the tangent that they mentioned touches the shape, which is most of the times the triangle. Where it touches the shape for the first time, there was always going to be an angle there. Well, that angle right there is the one that should be equal. If this was a tangent, you go to, this will be the chord, so you go with it to the circumference, which is this side over here. So all you need to prove here is that, let's call this one T1 and T2. You prove that T1 is equal to Q, and you'll be done proving it's a tangent. So if you can prove that, then you say, therefore, PT is a tangent And the reason you use is the converse tan chord theorem. Just like that. Very simple. Well, I hope you can. Let me just draw the third shape that they can say. Let's say they say, prove that, let me see how these shapes look like so I don't have the same type of shape. So let's have the one that comes from this side. So they say, prove that the tangent, I'm going to call that tangent PT again. The tangent PT, prove that line PT is a tangent to the circle passing through points ABT. So I'm just going to do this. If you can pick up, they want you to prove that PT is a tangent to a circle passing through ABT. If you can pick up which angles to prove without having to draw a circle, then I'm saying you are doing well. So in this situation, the first time the tangent touches the shape was right here. And then there was a line right there, and there was an angle being formed between what is said to be a tangent and the shape that you have. Then that is the chord you are using. Whatever it subtends on the circumference will be that B right there. So in this situation, you have to prove that T1 is equal to B. If you prove that T1 is equal to B, you're done. By the way, in case you are not grasping it, they are saying there is a circle that is passing through all those points. If there was indeed a circle that you could see, were you going to notice the tan chord theorem? Or maybe I shouldn't put that circle at all. If this was a circle, this was going to be an angle between a tangent and a chord, definitely, right there. So let's go into the actual question and see what I mean. Let's go to this one right here. So we want to prove a few tangents here. So we were told, however, in this question that AQ is already a tangent. We don't have to prove that one, it was given. Then we also have parallel lines, which are here. So prove that RA, I want us to find RA together. Please find it, it's right here. You will notice what happens here. Prove that RA is a tangent to circle ABQ. Try to find circle ABQ. I mean, those are the three lines. That's A, B, and Q. It doesn't look like it's a circle at all. There is a circle that we cannot see passing through those 3 points. But we don't have to always draw that circle with dotted lines to see what to prove. In this situation, the only thing that you want to prove, and for the sake of this lesson, let me do this. You want to prove that the angle, the tangent which they are mentioning, which is AR, meets the shape here at A, and there is always the angle that it will form. In this situation, it is A2. If it was the angle between a tangent and a chord, the chord we will be talking about will be AB. So prove that this angle will be equal to angle Q2. If you can prove that, then you're done proving that it's a tangent. So let's go and try to do it together quickly and figure out what's what. So find angles that are equal to A2 and find angles that are equal to Q2. So I am going to remove everything now so we can try to work. And please, because I've already named that A2, I may have to write those 1s and 2s. So if you look at angle A2, I can't help it but to notice that it is equal to P. I hope you are seeing the same thing. You see, with these parallel lines here, it's difficult to miss. But is it going to be helpful? A2 is equal to P right there. Before I write it down, I just want to see if this is going to help me in any way. Yes, I just noticed it will. So I'm going to write A2 is equal to angle P. And everyone can see that these are alternating angles, and that is QP is parallel to AR, like that. After we do that, let's remove those ones. We are done with the parallel lines. I want you to notice something else. There is a tangent right here. we were told that little thing that right there is a tangent. AQ is a tangent. There is a chord which is in contact with it, and I want us to use this chord right here. So Q2 happens to be an angle between a tangent and a chord. So to figure out what it is equal to, you go on both sides of this chord and then you draw it until you reach the circumference. As you can see, it will be this angle that is right there. So Q2 itself must be equal to P, and that is tan chord theorem. Okay, now these two angles are actually equal to P, so therefore I am seeing that A2 is equal to Q2. The moment I do that, I can say as a result of all of this, it means RA is a tangent to the circle. We can name the circle, what is the ABQ? And then you give a reason. Why is that? Converse tan chord theorem. That's how you do this one. Okay, that was your first example on proving a tangent. So I hope you are following. Let's see if we can do another one. Maybe it will be easier after that one. Let's go to question 2. We first of all use the given information as much as we can. We have a tangent. Were we given a tangent? No. We want to prove that AB is a tangent to this circle. So let's go and find AB. There it is. That's your AB. And now let's find what they are calling a circle. It usually forms a triangle or any other closed shape. So AED, so it's A, E, D. So do you pick up the letter where the tangent, the blue line, meets the shape, which is the triangle, for the first time? I believe you are seeing it. It is at this point A. That is where an angle is formed. So it's about this angle. If you can prove that this angle right here, and the chord that I am touching at this same time is actually this chord, then you go with it to where that circumference must be. So it means it's these two angles we have to prove. At this point, if you can prove that A1 is equal to D, you will be done with this business right here. So let's quickly figure out what it is that we are going to do here. So we want to prove that A1 is equal to D. That is our mission. So if we find angles that are equal to A1 and we find angles that are equal to D, we will be there in no time at all. So I am going to just mention those angles just now. Now, at this point, I can't help but to notice these two given things. So A1 is definitely equal to C here, because these ones are angles opposite equal sides. Okay, we were given that these two sides are equal. Okay, now we just proved that A1 was equal to C. Please notice there is a bow tie right here, which is very difficult to miss. So by doing this, I can see that angle C is actually equal to angle D as well. And those are angles in same segment. Okay, so now at this point, I can easily see that A1 is equal to D since they are both equal to angle C. So as a result of all this, I can now write AB is a tangent to circle AED, and my short reason, converse tan chord theorem. Okay, let's do this question here, the question 3 part. Let's see what we can do here. So if we were given, if ALB is a tangent to the circle, so we already have a tangent here. The question I want is actually question number C here, the one that we are proving that LM is a tangent to the circle. So but however, let's just do the top ones first. How are we going to prove that LM was equal to LP? these ones? Well, I believe you're noticing by now that it is these two angles that we have to prove to be equal. So if I can prove that M1 is equal to P1 in some way, then you don't have to actually write it. You can have it as a game plan somewhere. M1, prove that M1 is equal to P1. That's what you want to do. So how do you get there? Let's see how fast we can get here. I believe if I use L3, I'll get there fast. So using our tan chord theorem, L3 is an angle between a tangent and a chord LM. So it will be equal to this angle here at the circumference, which is P1. So I can mention that L3 is equal to P1, and that is tan chord theorem. Okay. After mentioning that L3 is equal to P1, I can also go and mention how the other angle we are interested in is M1. So I can now say, well, L3 is equal to M1. Please notice, let me erase the green so you can see what else I'm talking about here. So I'm going to talk about the parallel lines this time around. So notice there is a Z over here. These lines are parallel to each other. So definitely these two will be equal to each other. So we are saying that is because of their alternating angles in this situation. And since they're alternating angles, because AB is parallel to AMP here. So notice we have two angles that are both equal to L3. So that is this angle and that angle. So you can see that I can say, therefore, P1 is equal to M1. And the moment I do that, then I can conclude, I can make my conclusion that LM must be equal to LP, because those ones will be sides, opposite, equal angles. So this way of showing that sides are parallel, I think it's sinking in. What else was asked in this question? You were supposed to show that LN bisects M and P. To bisect is to divide into two equal angles. So this angle M and P was bisected by this line. So what it means is that this angle, you just have to prove that those two angles are equal to each other. You have to prove that N1 is equal to N2 in some way, and then that will be all that you have to do. So that's what is in your head, right? They shouldn't form part of your solution, but you have to have it somewhat somehow. So how do you prove now that N1 is equal to N2? Let's see if I can find a fast way of doing it. I don't seem to have a very fast way of doing it. I'm seeing that L3 will be equal to N1, and what else will be interesting? L4 will be equal to N2, but those are two different angles. I hope you are seeing a faster way, very fast. What did we prove initially? That M1 was equal to P1. So this one being equal to that one. So I'm noticing, however, that we have L3 here. I can mention that immediately, which is equal to N1. And then I just need something that is equal to N2 that is fast here. N2 will be equal to M1. Okay, that's fine. I'm going to use that method. So I am going to mention that L3 is equal to N1 firstly. And that is because of the tan chord theorem, right? Well, after I do that, I am going to now use the fact that we have already proved that M1 here was equal to P1, and M1 is actually equal to N2 firstly. So let's go and say, before I do that, I'm just going to say L3 is equal to M1. I think you're seeing that they are alternating angles. I don't like the fact that I am using many statements here. So let me know yours once you're done with this. So it's AB is parallel to MP here. Do you see where I am going? We are proving the alternating part. We just proved that this one is equal to that. Then I am now going to say M1, but let's create space. M1 is equal to N2. Those are angles in same segment. Okay, let me see if I'm close to where I want to go. Okay, m1 is equal to that, and okay, I think for you to understand well, I should make a conclusion on this statement. So we have two angles that are both equal to L3. So, but from those two statements, I can conclude that N1 is actually equal to M1 here. So it's a conclusion from these two statements. And at this point, I just also mentioned that M1 is equal to N2. So if M1 is equal to N2 and N1 is also equal to M1, so it means, therefore, it means N1 must be equal to N2. Please notice it's because they are both equal to M1 here. You don't have to really write that statement, that reason. So we proved it. We don't have to do more than that. Well, there is that last statement where we have to prove that LM is a tangent to circle M and Q. So let's just use this different. So if I say LM, this is LM, and then let's figure out the circle that they're talking about. That's M and Q. So M and Q, let's find M and Q. So M and Q. So we want to prove that that LM line is a tangent to that circle. So all that we really have to prove is that this angle right here, which is M1, is the angle between the tangent and what would be presumed to be the chord, and at this point it should be equal to N1. So if you can prove that M1 is equal to N1, you will be sorted. I think we proved that. So I'm just really going to say N1 is equal to M1. We have proved that. So if we proved it, we don't have to do it again. So what it means is that LM is a tangent, okay, to this circle, and you have to mention converse tan-chord theorem. Okay, so that's all you really have to do. Nothing so serious at all.